Okay, good morning everyone. So I'm gonna start with a couple of announcements. So as you all know that on Monday we're gonna have our first exam. If you're taking the exam in UMass Amherst, please show up at 9:20 a.m. outside the Gen Chem lab in ISB. If you're taking it in a proctor center, make sure that you be there on time, that you schedule with your proctor. Your proctor must have the access code by now. Bring with you, whether to UMass or to the proctor center, a photo ID, whether a UMass ID or your driving license. Otherwise, you will not be able to take the exam. Once you are there in the proctor center, or if you're in UMass Amherst, I'll take care of the rest. I'll let you know what you're gonna do. But for those who are taking it in a proctor center, you log into OWL using your usual username and password. Once you click in the assignment, you're gonna see exam 1 summer 17. Once you click on it, whether you are taking it in UMass or in a proctor center, it's going to ask you for an access code. That access code is not your OWL access code. It's what the proctor has as your access code. You're going to put in the access code in there, and you're gonna start your exam. I'm monitoring the IP address and I'm checking what are you doing exactly. So at no point, if you decide to leave the proctor center, your access code will not work anymore. So once you click on that, you're gonna get to the information sheet about the e-exam. I already uploaded one of that, which is just tell you what is the software. If you took the practice exam, whether the 1 hour or 4 hour, it's exactly the same software, the same interface that you've seen in the practice. So if you'd like to see how it would look like, just click on the practice exam, one of the practice exam, the 1 hour or 4 hour. Now, once you open that, your time would not start, your 70 minutes will not start until you click start the exam. So if you just sit there and you don't start the exam, your 70 minutes is not counting yet. So once you click start the exam, you're gonna see in here on the left margin of OWL 23 questions. The first one is not really a question. It's the reactivity chart for the benzene ring. So if you click on it, you don't have to answer it. And I made it clear that you don't need to answer it. Even if you answer it, it's not gonna add point to you. So that's the reactivity chart. If you'd like, you can write it down on a scrap paper or write some of it, but you can go back to it whenever you want during the exam. So in other words, don't expect that the proctor will give you the reactivity chart. The reactivity chart is in the exam itself, so that to make it easier for you. Now, as you know, the exam gonna cover 14, 15, 16. These are the mechanisms included in the exam. The practice exam is available on OWL. Now, exam study guide is already in OWL, and definitely the summary of reaction of chapter 16 is on OWL. So all the best of luck in the exam. So today's lecture gonna be all practice exam. So today's lecture is all about practice exam 1. The way that we're gonna do it so that you benefit the most is, if you're watching this video online, please stop it, go do the practice exam and come back here just to it will be more beneficial for you than just watching the lecture. For those who are online, stop the video, think about it yourself, then open the video and hear the answer. Let's start with the first question. So the most popular answer is A. A is the right answer. So in here, before we go to the easiest way to start eliminating some of the choices or to figure out the right one, I have a methyl NO2 and the Br on the benzene ring. I know that to have a methyl on the benzene ring, this is a Friedel-Crafts alkylation. And one of the limitations of Friedel-Crafts alkylation that there shouldn't be a meta-directing deactivator on the benzene ring. NO2 is a meta-directing deactivator on the benzene ring. So I have to do the alkylation before the nitration. Now the question, do I do the bromination first or the alkylation first? Now, none of the choices given the bromination is before the alkylation. So, in other words, I limited down that first I have to do the alkylation. Clearly, those two methods, I'm first adding the NO2, so I'm deactivating the benzene ring, then I'm doing the alkylation after that. And this is why both of these are wrong, because I already have a meta-director deactivator on the benzene ring, then I'm doing the alkylation. So method 1 is right, because first I have the benzene ring, I'm doing the Friedrich-Crafts alkylation. The benzene is not substituted, so I don't have to worry that there shouldn't be a meta deactivator or NH2 or NHR or NR2. None of these are there. Do I have to worry? Because one of the limitations of Friedrich-Crafts alkylation is rearrangement. Do I have to worry about rearrangement in this case? No, because it's one carbon. So I don't have to worry about the alkylation. Guys, and as I go, I'm just gonna do the revision for the other aspects of the reaction since it is a review session anyway. So the methyl is there. Next, the bromination. So the methyl itself is an activator, ortho, and para director. So what I'm expecting is both the bromination of the ortho plus the bromination of the para. So if you thought about that, you're right, but I'm assuming in this equation that I can separate the ortho from the para. So I done in the lab this step, I separated the ortho from the para, and now I'm gonna take the para and add to it HNO3 H2SO4, which is the nitration. Now this is an ortho para director, this is the ortho of it. This is a deactivator, yet also it is an ortho and para director. So in here, I have two groups. They are pointing to opposing position. The one activating, one deactivating. So the one that's going to form the dominant major is the nitration of the most activated one, or the more activated, which is the methyl. And that's end me up with the methyl NO2 and Br as the major, yet some of it will be the NO2 on this position, but that's okay also. But the major, the dominant major, is the one that is in the... Okay, let's go to the next one. So the most popular answer is A, and A is the right answer. So in the question, if you look at it, I underlined Friedrich-Crafts alkylation. And usually you're going to see that in the exam, because I'm bringing your attention. Please pay attention. This is not a chlorination, not a bromination. This is a Friedrich-Crafts alkylation. And once you hear the word Friedrich-Crafts alkylation, you should directly, if I'm you and if I were you and I'm doing the exam, the first thing I'll do on my scrap paper, I'll start writing what are the limitation of Friedrich-Crafts alkylation. Actually, I just want to point one thing, that once you get to the exam, as I said, your time, it's not going to start until you click the start button, so the 70 minutes will start. I just want to bring your attention that I don't mind if you take 5-10 minutes to write whatever you know on a scrap paper before you start the exam. Actually, I think this is a very good idea to do so. I'm saying that because some students usually report to me that, oh, I know the reactions before the exam. When I'm asked in the question, I even forget the basic material. So probably if you write what you know, just the basic, all the reactions that you know, before you even start, you have it before the stress of the exam itself. So I really don't mind if you want to take some minutes, even if you are in the Proctor Center. Your time not going to start. The exam time, the 70 minutes, is not going to start until you hit the start button of the exam. So please do so. And one of the things that you should write as on your scrap paper is a Friedrich-Crafts limitation for alkylation in here, and no meta deactivator, meta directing deactivators, and no NH, NR2 or NHR on the benzene ring. So this is what you should keep in mind. This is the first thing I would look at. Both benzene rings, none of them has any of these, which is good. Now looking at ring A, again, we're adding one equivalence in here. So only one position in both benzene rings gonna be alkylated. Ring A, it has this R, this is an R, this is like an ethyl, so you can consider that an R. It's activating, so on this one activating on ring A. On ring B, we have the OH and the R, so two activating groups. So I'm comparing ring A, one activating group, to ring B, two activating group. Definitely ring B is the most activated. Now between 8, 7, 6, 9, which is the most activated. So we know that R groups, so this is an R group on the reactivity chart, ortho and para directing, and the OH is ortho and para directing. So in other words, the OH and the R are pointing to opposing position. Which one gonna win? The most activating. According to the reactivity chart, the OH more activating than the R group. So which makes position, ring B, position 7 and 8 are the ones that's gonna be alkylated. Now, either 7 or 8, it's symmetrical. So whether it end up on 7 or it end up on 8, it's exactly the same. It's a symmetrical molecules. This is why I put 7 and 8 together, 6 and 9 together, because they are symmetric. Okay. Let's do this one. So A is the most popular answer. A is the right answer. So in here, I have benzene ring definitely substituted with KMNO4H3O+. So this is an oxidation reaction of a substituent on the benzene ring. We learned that the requirement for the reaction to take place is at least one benzylic hydrogen. So looking at this benzylic carbon, and what I mean by benzylic carbon, the carbon that is directly attached to the benzene ring. So for that one, it has 1, 2 bonds. So clearly it has 2 hydrogens. So that one with KMNO4H3O+, or sometimes H+, or sometimes H2O, or sometimes just heat. Any of these are exactly the same. So this should go to the benzoic acid. This should be oxidized all the way to the carboxylic acid. But let's check this carbon in here. This carbon has 1, 2, 3, 4 bonds. So clearly it has no benzylic hydrogens. So this one should not, this alkyl, which is tertiary butyl, should not be affected by this oxidation. So no benzylic hydrogen. So it shouldn't be affected. So in other words, this should be oxidized all the way to carboxylic acid, and this one should stay as it is, which makes 3 the right answer, which is A in the choices. Okay, let's go to the next one. Okay, so 5 is the most popular answer. 5 is the right answer. So the first thing that you should recognize in here, that this is a nucleophilic aromatic substitution rather than EAS. So it isn't electrophilic aromatic substitution, it's a nucleophilic aromatic substitution. And how do you know that? It's from the OH minus. The OH minus is not an electrophile, it's rather a nucleophile. We learned that for such type of reaction that I need a good leaving group, which is available in here, but for the OH minus to replace the good leaving group, which is either ClBr or I need a meta-directing deactivator on the ortho and the para. In here, I have a withdrawing group, which is in a sense the deactivator meta-director, but it is on the meta. And we said for the substitution to take place, the withdrawing group should be ortho or para from the leaving group. So this is why there is no reaction. So the point in here is to figure out that this is a nucleophilic aromatic substitution from the NaOH. Sometimes this is written as NaOH. The sodium is just a counter ion, or KOH. It's exactly the same. Okay, let's go to the next one. 5 is the most popular answer. 5 is the right answer. So I'm starting with a benzene ring. And I'm adding, so this ClCO, that is a double bond OCH. And when I have CH3 between two brackets and then a 2, that means there are two methyls that are connected to this carbon. This is what this CH3 between. So I have methyl, methyl, and I'm adding AlCl3. So this is a Friedrich-Crafts acylation. The benzene ring is not substituted, but if it was substituted, there shouldn't be a deactivator meta-director. But in this case, it is not substituted, so I don't have to worry about that. Do I have to worry about rearrangement in Friedrich-Crafts acylation? Will there be a possibility of rearrangement? No, it's only Friedrich-Crafts alkylation where I have to worry about rearrangement. In acylation, whatever I start with as an acidic chloride, the carbon of the carbonyl will be attached to the benzene ring with no change. Now the next step is Cl2FeCl3. We know that this group is a deactivator and it is a meta-director. So it's going to direct it either to this meta position or this meta position. So I'm going to put the Cl on the meta here. Now the next step is H2 Palladium Carbon. We learned that H2 Palladium Carbon does not affect the benzene ring itself, but it will affect an aryl ketone. In other words, it's the C double bond, the carbonyl that is directly connected to the benzene ring. It will go all the way from the C double bond O to CH2. Now, I just want to ask a question. Why we didn't directly add this as an alkyl halide to the benzene ring? Since this is what I want, why didn't I just have the benzene ring and then I added this as my alkyl halide? Why did I have to do acylation then reduction? Go ahead.
Because carbocation rearrangement.
Very good. Very good. In this case right here, this will have a carbocation in which a hydride shift will take place from this one to this carbocation, and I'll end up with a tertiary-butyl. So in other words, if I'm starting with this, the major will be a tertiary-butyl benzene rather than this one, than just this attacking the benzene ring. So this is why in here it's done acylation followed by reduction. Now the next step is nitration. Now this one in here is a activator, ortho and para director. These are the orthos. This is the para of it. This Cl is a deactivator, yet it is an ortho and para director. These are the orthos, and this is the para. In here, I have two groups. They are pointing to the same position. Would this be a major, like nitrating this position in here be a major? Why not? What's about this position in here? It's a sterically, hindered position. So what I'm expecting is the NO2 to end up either on NO2 on this position plus NO2 on this position. Now the next step is H2 Palladium Carbon. So if I add H2 Palladium Carbon to this one, I'm gonna end up with the NO2 will be reduced to NH2. So We learned that H2 palladium carbon reduces NO2 on a benzene ring to an H2, and the C double bond O on a benzene that is directly connected to the benzene ring, thus mean a benzylic carbonyl into a CH2. So it reduced that to an NH2. Now let's see if I have H2 palladium carbon in here. Now, if you look at both products, only one of them is given as a choice in the choices I gave. And that doesn't mean that the other one will not form, but in the way that I asked the question, I put only one of them so that I don't confuse you with both. But if both of them were stated in the multiple choice, you should choose two, the both of them. Does this make sense? Any question about any step I've done in here? Now, if I'm preparing for the exam, I would take the starting material and the end material and try to do it myself and see, can I figure out the steps? So in other words, you can flip this question if you want to prepare more for the exam or do some more practice. Okay, let's go to the next slide. So 2 is the most popular answer. 2 is the right answer. So in here, I'm starting with this cyclohexene. The first step, MbSUVCCl4. These are the conditions for the bromination, either for an allylic position or a benzylic position, right? So if I have something benzene with, I don't care what's R, but I have a benzylic carbon that has at least one benzylic hydrogen, I can add MbSUVCCl4 and brominate that position. The same for the alkene, so I'm brominating this position in here. Now, clearly this is a symmetrical molecule, and when I add MbS, that means I didn't say 2 equivalents. I'm assuming just I'm adding 1. And both positions are symmetrical, so whether I brominate the upper allyl or the lower allyl, I'm exactly going with the same thing. Now, the next step, tertiary butoxide, which can yield the elimination of this Br and this H. And these two steps are the very usual steps to prepare conjugated diene. Always these two steps what gonna yield the conjugated diene. Now, ozonolysis followed by zinc H3, or the two steps are mainly ozonolysis. In ozonolysis, wherever there is a C double bond C, it's gonna break to form a C double bond O. So I'm gonna call this A, B, C, D, E, F, and I highly recommend that you do so if you're still kind of get confused with the number of carbons. So this is A and B. So wherever there is a C double bond C, it's replaced with a C double bond O, plus I have F, E, D, and C with a double bond O, which make 2 is the right answer. Does this make sense? Now, what if you're given, let's say, the same one, but 2 equivalents of MbSUVCCl4? So in this case, I have enough to brominate both positions, this one and this one in here. Okay? So this is if I have 2 equivalents. Then tertiary butoxide, if I add the tertiary butoxide to this, so the Br and the H from this, the Br and the H from this, I can end up with a benzene ring. Okay. Does this make sense? Okay, so if nothing is mentioned, you're kind of assuming 1 equivalence. If I say 2 equivalents, then 2 positions will be brominated. Okay, let's do this one. So the most popular answer is 2. 2 is the right answer. So this is about aromaticity. We're gonna start one by one. Each one kind of, we're gonna do a quick review for the concept. So the first one, for something to be first considered aromatic or anti-aromatic, first it should be cyclic, fully conjugated. So this one, number 1, yes, it is cyclic, full conjugation. Now the second step is counting the number of electrons. We're counting the electrons in the pi bonds. 1, 2, 3, 4 electrons. 4 is anti-aromatic, which is part of the 4n rule. Now going to B is a heterocyclic compound. So we have a cycle. Yes, it is cyclic, fully conjugated. The question is, would I consider the lone pairs of the nitrogen part of the system, and I mean by the pi system, or not? We said that if the nitrogen is double bonded, we're not gonna count the lone pairs of the nitrogen. Why? Because they are sitting in a p orbital that is perpendicular to so this is the nitrogen, the p orbital for this, they are in a p orbital in there, that in an orbital in there that is perpendicular to the p orbitals of the pi system. So physically they are in different planes. So there is no way that the lone pairs of the nitrogen, when it is double bonded, to be counted. If the nitrogen was single bonded, I'll count the lone pairs. So in here I'm counting 1, 2, 3, 4, 5, 6. Don't count. Nitrogen is double bonded. So total of 6 electrons, 6 is aromatic, 4n plus 2 rule. Now the last one in here, I'm gonna redraw it. Mainly it is a benzene ring, right? It doesn't matter what's connected to it. It's a benzene ring. We've seen in chapter 16, it doesn't matter if I have an NO2 on the benzene ring, or an SO3, or a double bond, or tertiary-butyl. Doesn't matter. At the end of the day, it's still a benzene ring. Now, is this double bond conjugated with the benzene ring? Yes. Am I gonna count the electrons of that as part when I'm counting whether it is aromatic or not? No, because I only count the electron inside the fully conjugated cyclic system. I don't count the electrons from that pi bond outside it, from this pi bond. Does this make sense? So yes, this double bond is conjugated with the benzene ring, but for the sake of aromaticity, whether this is aromatic or not, I'm gonna judge it only by the electrons inside the cycle. So yes, it's cyclic, fully conjugated, 1, 2, 3, 4, 5, 6 electrons. It is aromatic, which make 2 is the right answer. Okay, let's do this one. Popular answer is C. C is the right answer. So in here, I have an unsymmetrical conjugated diene, and I'm adding 1 equivalence HBr. I'm asked about the 1214 from the most stable carbocation intermediate. So as usual, there are, since I'm gonna alphabetize that A, B, C, D. So if I add the hydrogen, the H plus to carbon A and B double bond A and B, it's gonna give me a carbocation system different than C and D. Now, definitely I taught you at the beginning that, oh, do each one and start figuring out. But it's good also to have expectation before you get into the details. Most of the time, there are exceptions, but most of the time, if you start with the alkene that is more substituted alkene, that one that's gonna form the most stable carbocation system. Most of the time. There are exceptions. I'm not gonna go to them. So it is most of the time, if you add it to the more substituted, it's gonna give you, because if you add it to the more substituted, you're gonna have a better carbocation, a more stable carbocation. With that said, and in here, AB is more substituted than CD. So if I add the H plus to AB, I'm expecting, just as an expectation, it might be the most stable carbocation system. So adding H plus to carbon double bond AB, it will yield, so I'm adding it Markovnikov, so I added the H to carbon A because it's the carbon that is richer in hydrogen. So I'm gonna end up with the carbocation in here, which is tertiary allylic. The resonance structure The resonance is always the pi electrons in an allylic conditions like this. The electron will flow from the high density of electron to the low density of electron. So now I have a secondary allylic carbocation. So this is if I add it to A and B. Now I'm going to add the H plus to carbon C, carbon D. Now both C and D has exactly the same number of hydrogens. So I have to try both. But with experience now you know that if I add the hydrogen to C, I'm going to end up with a secondary carbocation which is not allylic. So this is why I'm deciding to add the hydrogen to carbon D instead. Definitely if you want to go slow with that, you can add it to both. One time to D, one time to C, and see what you're going to end up with. So this is a secondary allylic carbocation. It has a resonance structure. To primary allylic, to a secondary allylic, so it is C, B, A, to a secondary allylic. It becomes clear that the system that we expected, which is adding the H plus to the more substituted alkene of the conjugated diene system, gave us the most stable carbocations. To get the 1,2 is when the Br minus gonna attack this carbocation. So it is the 1,2 because the H and the Br are added to carbon 1 and 2, not iopacking, but in the diene system. If I add the Br minus to the resonance structure of the intermediate carbocation, that's the one that's gonna give the 1,4. So the position from the H and the Br is 1,4 from each other. So we call this the 1,4 adduct. So this is the more stable carbocation system. Now, the question can be, give me the major product at low temperature. Which one from the most stable? Always from the more stable carbocation. So which one is the major at low temperature? The 1,2. Which is the major at high temperature? The 1,4. Which one is the kinetic product? The one that forms faster? 1,2. Which is the thermodynamic product? The 1,4. So I can ask the question in so many ways. Actually, I can go back here and say at low temperature. I can put a condition here at low temperature and ask what is the major product. So the major product is the 1,2. I can put in here high temperature. So what I mean is the 1,4. Then the question is, give me the major product. So keep an eye on that you need. If there isn't a condition, that's one story. If there is a condition like low temperature or high temperature, that's another story. Does this make sense? Let's do this one. So in here, so the right answer is A. A is more acidic, or compound A is more acidic. Whenever you're asked about acidity, whether in the context of this chapter or in any other chapter later on, you're drawing the conjugate base. The conjugate base is a carboanion in this case, not a carbocation. You're going to get exactly the opposite answer if you do a carbocation. So I'll draw the conjugate base of the first one. If you forget whether it is a conjugate base, the conjugate base is carboanion or carbocation, think about it that the H left as H plus. That means it left its electron behind. This is why it is H plus. And this one, I'm just going to put it right here as this. So this one in here, it's 1. It's cyclic fully conjugated. The number of electrons, 1, 2, 3, 4, 5, 6. 6 electrons aromatic. Compared to this one in here, 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons, and definitely it is cyclic fully conjugated to 8 electrons and T aromatic. So in other words, A is much more acidic because it's forming more stable conjugate base. The more stable the conjugate base, the more acidic is the compound. Definitely, I'm not saying in here that those are as acidic as HCl, a strong acid, or even carboxylic acid. I'm comparing the acidity of both of these two together, but not to an acid in the sense of HCl. Let's do this one, and this is an easy one. Mainly, this is an alkylation of the benzene ring, and the point in here that there will be no rearrangement. Now, this in here, CH2, CH, and the Cl, so this carbon has 1, 2, 3, so it has a double bond. The point in here is just to remind you that if I have a benzene ring and I have a vinyl, in this case it's this one, there will be no reaction in here. That vinyl chloride will not undergo Friedrich-Crafts alkylation. So make sure that you know that. Okay, so even if I did the first step followed by H2 palladium, it wouldn't work. Okay? Let's do this one, naming. So clearly B is the right answer, which is only this. So mainly I put this just a quick revision for all the IUPAC rules of benzene. So if the chain, the alkyl chain connected to the benzene ring is longer than the benzene ring itself, that means 6 carbons and more, I'm going to consider the benzene as a substituent and this to be the main chain. The rules are exactly the same. Find the longest chain, give the substituent the longest number, the smallest. The substituent the smallest number possible. So 1, 2, 3, 4. So the mistake in here, it should be 4-phenyloctane rather than 5-phenyloctane. When it comes to the second one, I have COO, NO2, and Cl on the benzene ring. We know that COOH on a benzene ring has a parent name, which is benzoic acid, so that part is right. Now I have chloro and nitro. Now I have to go numbering clockwise or counterclockwise and find to give the substituent the lowest number possible. Since benzoic acid is part of the name, so this is number 1. If I go 1, 2, 3, 4, 5, 6, or I can go 1, 2, 3, 4, 5, 6. So if I'm going the green way, 3 for the chloro, 5 for the nitro. If I go the red way, 3 for the nitro, 5 for the chloro. When I have both ways will give me the same numbers for the substituent. Which one should win, the green or the red? How do I judge that?
You can go with alphabetical order.
Alphabetical order, and chloro, and this is nitro. So I'm gonna go with the green one because it's given 3 for the chloro, 5 for the nitro. And in addition to that, there is another mistake in the name that it isn't alphabetical order. So the right name is 3 chloro, 5 nitro, always a dash between a number and a letter, benzoic acid. Now, the last one, phenol is a part of a system. The NO2 is not. It's called nitro. They are 1,3 from each other. It's meta-nitrophenol or am-nitrophenol. So that's right. Go ahead. Okay, let's do this one. B is the right answer. So this is a very simple question. I have a methyl on a benzene ring. This is activating ortho and para director. These are the ortho. This is the para. I'm doing nitration, adding an O2 to the benzene ring. So this is the ortho, this is the para. So 1 and 3 are the right answer. Let's do this one. So A is the right answer. So the whole idea in here is just to point out a strictly hindered position. So this is tertiary-butyl. As you know, it's a very bulky alkyl. It is activating ortho and para director. So yes, this is the ortho, this is the para of it. This is methyl, which is activating ortho and para. This is the ortho, this is the para of it. So now, yes, this position is activated from a thermodynamic point of view, but it is strictly hindered. And it's, if ever, it's going to be substituted, it's going to be the minor. So now the BR, so 1 is definitely not the major, 2 is the BR is on the meta. 3 and 4, they are on the ortho or the para and not in the sterically hindered position. So those two are the majors. So in here, just I'm pointing to the fact that to remind you that there is a sterically hindered, the position on a benzene ring between two substituents is a sterically hindered. And I made it a little bit more extreme in here with the tertiary-butyl, which is a very bulky molecule. Okay, let's do this one. So B is the right answer. So in here I can say which of the following compounds is the most reactive with SO3H2SO4. I can do it nitration, chlorination, bromination, it doesn't matter. Mainly I'm asking rate them according to the reactivity chart. Which substituent on this benzene ring gonna make the benzene ring the most activated? Actually, let's take it a little bit further. Let's rank them. So phenol is more reactive than a benzene ring without anything on it. How I'm knowing that? I'm going back to the reactivity chart and figuring out where is the OH. Then I have a benzene without any substituent on it. That means with an H. So H. Then after that, the halogens, bromine being one of them, more reactive than an O2 on a benzene. This is if you're asked to rank it. It doesn't matter what's the reaction in here, sulfonation, bromination, nitration, as long as it isn't a nucleophilic aromatic substitution. It's not an AOH. Other than that, you go to the reactivity chart, figure out the position of the substituent on the benzene ring on the chart. Okay, let's do this one. So B is the right answer. This is a benzene ring with 1 mole of Br2. For the reaction to take place, it needs FeBr3, and this is why it is no reaction. It's mainly, as we talked before, that a Br alone would not be enough for the reaction to take place. So this is why we need FeBr3. Does this make sense? Okay. I think this is the last question. So 4 is the right answer. Mainly that goes back to the UV vis, that mainly the delta E between the HOMO-LUMO is inversely proportional to the wavelengths of the light that is absorbed by the molecule. So in other words, for it to be the longest wavelengths, it should be the lowest difference between the HOMO and the LUMO. And when we looked at that, we found that the more conjugated, the higher the degree of conjugation, the lower is the difference, or the smaller is the difference between the HOMO and the LUMO. So the higher the conjugation, the higher the degree of conjugation, the smaller is the difference between the HOMO, the energy difference between the HOMO and the LUMO. So in here, 3 conjugated bond, 2 separated double bonds, 3 conjugated, but clearly one of the alkene is more substituted, so it is 3 conjugation and it is more substituted than 2 conjugation. So it became clear that the longest, the one that has the highest degree of conjugation, is A and C, but C is more substituted, the substitution adds stability, so C will be longer than A longer than D because D is 2 conjugated, and B gonna have the smallest wavelengths or the shortest wavelengths because the difference between the HOMO and the LUMO is the biggest. So that goes back to the UV and the idea of stability of conjugated diene. As you've seen in the practice exam, some questions are very simple, just pointing to one concept. Some of them, like the multi-steps, is more couple of different steps, and this is how you're gonna see the exam. Some is just like 2 steps to get the product. Some they are more sophisticated than just a quick question or one concept in there. So I highly recommend that you take the practice exam one more time. If you're done the 1 hour, take the 4 hours, and once you're done, you should go to the intensive practice. In the intensive practice, it's very close to the challenging question that you will be asked in the exam. Now, in those challenging questions, you're asked, put A, B, C, like what are the steps? But for the exam, all the questions in the exam are multiple choice questions. So I'll change the question into multiple choice and ask it. But the level of the concept is the same as between this practice exam intensive. And you're going to see some questions, they are almost the same as the eye clickers that we've done in class, in the concept, not the same structure, but concept-wise, they are very close to that. Have a great weekend and all the best of luck for exam 1.